Hi again, everybody. Welcome back. This example 10.9 is actually dealing now with rotational acceleration. Or I should say, angular acceleration. A constant. This is actually kind of funny. A constant acceleration. We can have constant accelerations, right? But what's not constant is velocity. So the angular velocity is not constant. Okay? Just like if you have a linear acceleration, linear velocity is not constant. But the angular acceleration is. So the rate at which it increases its angular velocity or angular speed is a constant rate. And that is alpha, of course. It might wind up looking like x's with the... I'm trying to make it more round. There we go. Alpha is 95.0 radians per second squared. That's our angular acceleration right there. All right. So we want to know what the magnitude of the resultant, you might say, of the centripetal, tangential, and total accelerations of the bottom of the tube are when the angular speed is 8 radians per second. Okay, so this right there equals 8.00 radians per second. Okay, so this is curving around like that. Okay, and so we're just going to pretend, I'm going to make a little red dot right here. Imagine that being like a blood cell at the very bottom of the tube. And again, this is kind of an extension of the previous problem, but it's at the very bottom of the tube. So that radius is going to be the same radius as it was before. All right, and so let me do this in a different color. Well, I'll do it in red. All right, so imagine the center right there in this radius equals 0.0907 meters. Okay. And so at this point it has an angular velocity. Again, that's an omega, it's not a W, of 8 radians per second. It has, I'll do the acceleration in blue. It has a centripetal acceleration, A sub c, and it has a tangential acceleration, A sub t right there. So what we want to find is, at this speed, okay, what is the resulting, you might say the magnitude of these two accelerations at right angles to each other? What do they come out to be if we were to kind of combine them into a single magnitude? Okay, so let's solve for... well, we want to find all of them, so let's find our centripetal acceleration first, all right, A sub c. Well, centripetal acceleration, let's do this in blue. A sub c, right there, is what? Well, that is r times omega squared, right? Well, we have both of those values. In fact, we got that from the previous problem. In fact, let me just skip back to that one real quick because I still have it done. What was our centripetal acceleration? Oh, no, I'm sorry. We can't do that because... no, we can't do that. All right? I'll tell you why. Because this is the angular speed we're dealing with right now. So let's just plug in the values that we have right now. We do know that the radius is the same. So the radius is 0.0907 meters times now this velocity right here, angular velocity, 8.00 radians per second. That's going to give our centripetal acceleration at that speed, 0.0907 times 8.00. That is 0.7256 meters per second squared. It's meters per second squared, not radians per second squared, because this is a... you might say it's a linear acceleration, but it's directed linearly towards the center, the centripetal. All right? Let's find now the tangential acceleration. Tangential. All right? A sub t. That is, our tangential acceleration is radius times the rotational acceleration, r alpha. Well, we know that too. 0.0907, that's a 9 right there, times this rotational acceleration, which we've been given, 95.0. That will give us our tangential acceleration, 0.0907 times 95.0. That is 8.62 meters per second squared tangentially. That's this one right here. All right? And the total acceleration. So just A, what would that be? Well, we have these at right angles to each other, right? Here's centripetal, there's tangential, they're at right angles. And so we're going to use our Pythagorean. That's going to be the square root of AC squared. I should probably put the t first, sorry. AT squared plus AC squared. So that's going to be the square root of 0.7256 squared. I put too many digits on that. Plus, what is our tangential acceleration? 8.62 squared. Square root of all that stuff. It's just like we're finding the resultant vector. 0.7256, probably too many digits, plus 8.62 squared to the 1/2 power. That's like taking the square root. That's going to be 8.65 meters per second squared. That is our total acceleration, which is the combination of these two. All right. Now the last thing we want to do is find the angle. That's part B. What angle does the total acceleration make with the direction of motion at this speed? Oops, sorry. At this speed right here. So part B, we want to know what that phi is right there. Well, that's going to be the inverse tangent of what? It's going to be the centripetal over the tangential. So AC over A sub t. All right, so inverse tangent of, what's our AC? 0.7256 over 8.62. Inverse tangent of that, 8.62. Sorry, I'm doing this in real time, so it takes me a second here. 4.81. Oh, you know what? Do I have that in, what mode am I in? I'm in degree mode. Haha, that is 4.81 degrees. So that's this angle right there. That's our phi. Let's convert that to radians. So that's times 2 pi. Okay, let's convert that to radians real quick. Times 2 pi divided by 360 degrees. So that's 0.084 radians. All right, so those are, if you want degrees, there you go, but we should stay consistent with radians. So that is, in fact, let's stay with degrees, because radians, we're talking about going around in a circle. This is really the angle that it is measured, that this total acceleration is offset from tangential acceleration. It's different from a rotational angle. Let's keep this in degrees, but that would be the conversion there anyway. Okay? So that's our angle phi and our total acceleration, 8.65 meters per second squared. All right, that's example 10.9. Thanks for following along. If you have any questions, let me know. And if not, I'll see you on the next one.